Hello everyone, thank you for watching my primer video for IMS2023. My name is Hua Wang. I'm a full professor at Swiss Federal Institute of Technology in Zurich, Switzerland. In my following talk, I'll give you an overview on the millimeter wave power amplifier designs for 5G and 6G wireless communication. I will start by introducing the state-of-the-art performance of modern millimeter wave power amplifiers with a particular focus on silicon-based PAs. Many millimeter wave applications now rely on phased arrays, which make low-cost, medium-power silicon PAs often a preferred technology of choice. Next, I will present the key technology challenges particularly relevant to the 5G, 6G communication applications. Finally, I will show several example power amplifier topologies and designs as promising candidates to address these applications. Let us start with the introduction of the state-of-the-art performance of modern millimeter wave power amplifiers. Power amplifier is the last active circuit stage in a wireless transmitter system to interface with antennas. To generate sufficient signals for wireless transmission, power amplifiers are needed in most wireless systems, including mobile devices, fixed-point wireless, radar and imaging systems, and satellite communication systems. To start, maybe we can ask some fundamental questions. What is a power amplifier? Or to be more specific, when an amplifier should be called a PA? Is it necessary to generate a watt level of power to be considered as a PAs? Or perhaps PAs are the amplifier designs where the conventional wisdom of conjugate matching is no longer being used? Maybe PAs are amplifiers that will generate large nonlinearities and can cause some damages. A general PA schematic is shown here. This is a two-stage PA with a driver and a power output stage, together with the input, interstage, and output matching networks. In general, the PA can be separated into the active circuit designs and the passive network designs. The active circuits deal with device performance, PA classes, waveform shaping, and device stability, as well as reliability. The passive networks will cover impedance transformation, power combining, also waveform shaping, and bandwidth filtering performance of the PA. For PA designers, we need to specify the output power level. The PA output power is typically determined by the regulation and the link budget specified by the phase transmission equation. Knowing the required receive power, antenna gains, distance, and carrier wavelengths, the required output power can be calculated. For RF PAs, the typical power levels are often between 20 to 26 dBm, depending on the standards, with some exceptions such as Bluetooth low energy applications. For millimeter wave PAs, the required PA output power has a direct relationship with array size and the total equivalent isotropically rated power, ERP. Given an ERP value, a small array requires a larger PA output power. On the other hand, a larger array reduces the element level PA output power, but it requires a large panel size, sharper beams, and often more system overhead. In this table, the element level PA output power values for different applications clearly show their relationships with the ERP and their array sizes. It is very useful to see the state-of-the-art power generation capabilities by using solid-state devices. Using the ETH PA survey, the reported output power of PAs in different technologies from 2000 are plotted here versus the carrier frequency. At low frequencies, the output power is typically limited by the applications and regulations. When the frequency goes higher, we start to see a monotonic decrease of output power due to device limitations. Interestingly, the trend roughly follows minus 20 dB per decade that matches very well with the Johnson's limit. This plot is useful for system designs to estimate the achievable PA output power for a given technology at a given frequency. In summary, it is indeed challenging to achieve high output power for high frequency operations. The second challenge is the output power versus efficiency. Silicon devices have limited output power and often limited voltage swing. For a larger output power, one needs to increase the output RF current as well as reducing the load resistance. This means we need larger devices or putting more devices in parallel for power combining. This also requires a larger impedance transformation ratio by the PA output matching network. Both of them will introduce more losses and degrade the overall PA efficiency. The figure on the right summarizes the peak PAE versus maximum output power for 20 to 50 GHz PA in silicon reported from 2000 to present. At the lower output power level, the PAE is around a constant value of 45% for 20 to 50 GHz, which is limited by the silicon device intrinsic efficiency and the passive loss. I call it the device limited regime. However, when we move to higher output power level of 23 dBm and above, we'll see a very rapid degradation of efficiency. This is because at this higher output power level, a single silicon device can no longer deliver the power required. So more devices and complicated passive combiner networks are needed, which will introduce more power loss. I call it the combiner and the network limited regime. Therefore, it is challenging to achieve PAs with high output power, high efficiency, and a compact area. Record the PA output power versus array size chart. We can see that many applications, including the handset and some base stations for 5G and millimeter applications, have set their output power level close to lower than 23 dBm. And this output power level suggests that the silicon will be a capable technology for these millimeter applications to deliver such low to medium power levels with a very competitive efficiency. If we look at other 3-5 compound PAs at this frequency range, the gallium arsenide PAs can typically generate more than 5 to 10 dB output power than silicon PAs, while the gallium nitride PAs can generate more than 15 to 20 dB output power and reaching the power level of over 45 dBm. By the way, I also want to mention that there has been a rapid growth of millimeter wave gallium nitride PA designs in recent years, which resonate very well with the continuous advance of gallium nitride technologies recently. Now, if we again look at the PA output power versus array size and summary chart, and we can see the 3-5 technologies are really needed for high power base station applications. There are a lot of exciting R&D activities, especially on millimeter gallium nitride PAs recently, and they will play a big role in 5G and potentially beyond 5G applications. Due to the limited focus of and the scope of this talk, I will not be able to cover them here. But for those who are interested, I encourage you to look at recent literatures and learn about these new designs. We can further look at the PA efficiency versus the carrier and frequency. This plot shown here is the peak PAE versus carrier frequency over 20 to 240 GHz in all technologies. We can see that at 20 to 30 GHz, the silicon PAs can achieve high efficiency of 50%, while silicon and indium phosphide PAs can achieve efficiency even higher than this value, but the achievable efficiency will drop rapidly over frequency down to around 10% in the D-band frequency. This fast efficiency drop is due to both limited device gain and the limited output power capabilities at a higher frequency. However, higher frequency communication typically will need arrays with large scales and more densely packed elements, which are challenging for thermal management. So therefore, another challenge for PA design is how to achieve high efficiency at this high carrier frequency for large-scale array applications. Finally, the spectrum is crowded at the gigahertz legacy bands, as we know, while millimeter wave frequency and often assign multiple non-contiguous bands for the applications. For example, millimeter wave 5G applications uses different bands in different countries and regions to support multi-band, multi-mode, and international roaming. Wideband or frequency reconfigurable PAs are often needed. On the other hand, broadband operation often has trade-offs with output power and efficiency. To summarize, we can use a PA design hexagon to highlight the challenges and the trade-offs among these performance metrics. This level of complexity actually makes the PA design both challenging and full of innovation opportunities. Next, I will present several key technology challenges particularly relevant to the 5G, 6G communication applications. Before we talk about the challenges for 5G and 6G wireless communication, let's first understand their spectrum. For the 5G, for the scope of this talk, we are here mainly focusing on their millimeter wave FR2 bands, since the 5G sub-6 GHz bands are more or less the extension of the existing 4G bands at gigahertz frequencies. The millimeter wave 5G FR2 bands typically contain 28 GHz, 26 GHz, and 39 GHz, as well as 24 GHz for different countries and regions, including US, China, and Europe. For the 6G, in this presentation, we are mainly looking at sub-millimeter frequency bands, including the W band 75 to 110 GHz, D band 110 to 170 GHz, and G bands 240 to 250 GHz. It should be noted that the 6G also includes the FR3 bands from the 12 to 18 GHz, which is viewed as the further extension of the gigahertz RF spectrum. When we design the active devices for millimeter PAs, they really deserve additional attention. This is because the fundamental challenges in many millimeter wave PAs is actually the limited device power gain. For a two-port active device, its small signal power gain can be expressed as follows. From lower frequency until the stability inflection point, the stability factor K is typically less than 1, so the device is not unconditionally stable, and we can only obtain its maximum stable gain as MSG. Beyond the stability inflection point frequency, due to the lower device gain, it becomes unconditionally stable with K factor larger than 1. The device then offers maximum available gain MAG. When the MAG crosses 0 dB and the frequency at that point is called Fmax of the device. In reality, the device gain and Fmax highly depend on the device layout, biasing, and also the matching. The gain of a 45 nanometer CMOS SOI power devices is shown on the right for the Class A and Class AB biasing. Although Class AB may achieve a higher device drain efficiency, it degrades the Fmax from 334 GHz to 262 GHz, and the gain at 140 GHz drops from 5.6 dB to 4 dB, which will come back and degrade the efficiency. With that, I have listed a few key challenges for 5G and 6G PAs that will be presented in this section. So namely, the trade-off between PA linearity and the modulation efficiency, the array operation and the PA footprint for 5G PAs, and the limited PA power density as watt per millimeter square for 6G PAs. I'll explain each of them in the next few slides. Let's first start with the PA trade-off between linearity and the modulation efficiency. We know that a channel's peak data rate is determined by the channel bandwidth, number of spatially separated paths or beams, and the complexity of the modulations, as well as the overhead. The channel's ultimate capacity is limited by the bandwidth, spatial paths or independent beams, and the channel SNR. Therefore, this motivates us to use millimeter wave frequencies when there is more available spectrum. At the same time, the MIMO operations and the complex modulations are needed to boost the data rate. Therefore, we would expect and future millimeter wave communication links will extensively use spectrally efficient modulations at gigabit per second high data rate. This involves high-order QAMs, OFDMs, and carrier aggregations. As a result, this poses stringent requirements on transceiver front-end linearity and SNR. This aspect drives the need for high linearity millimeter wave PAs, preferably without using DPD. Reducing the large and the signal distortion of AM to AM and AM to PM nonlinearity, therefore, is also a very popular research topic for millimeter wave PAs presently. Moreover, These spatially efficient modulations often lead to large peak-to-average power ratio (PAPR). For a 64-column signal, the time domain amplitude waveform is shown on the left, which, while its amplitude probability density function is shown on the right. It can be shown that there is roughly a 6 dB to 7 dB PAPR for these 64-column signals, depending on the waveform shaping. Therefore, during the modulation operations, the average output power of a PA is its power backup efficiency curve being scaled by the probability density function of the modulation amplitude, and then being integrated over the entire power range. Approximately, we can say that the average PA output power here is 6.5 dB lower than the peak output power of the PA when amplifying this 64-column signal. Therefore, for most wireless communication applications, the PA efficiency at the power backup is as important as this peak efficiency, if not more important. This is the reason why advanced PA architectures to boost backup efficiency, such as Doherty PAs and out-phasing PAs, have been a critical research topic, and they are gaining more attention for 5G applications. We can clearly see that different modulations have different PAPRs. Depending on the waveform shaping and the signal clipping, the PAPR ranges from 5 dB for a QPSK single carrier signal to 7.1 dB for 64-column single carrier signal, and to 11 dB for 64-column OFDM signals. And there are multiple standard ways to quantify the PAPR of a modulated signal. One of them is given by the so-called CCDF, and the complementary cumulative distribution function. It measures the probability of the signal to be at or above a given power level in dB relative to the average power. A plot here shows a modulation signal has 10.8 dB PAPR for 0.1% CCDF, while after signal clipping, its PAPR is reduced to 8 dB for 0.1% CCDF. As an example, a 5G NR-FR2 1cc 64-column signal is shown here. It has a 9.6 dB PAPR at 0.01% CCDF, while the peak PAPR is 12.32 dB. As another example, a 5G NR-FR2 2cc 64-column signal is shown here. It has a 11.8 dB PAPR at 0.01% CCDF, while the peak PAPR is 14.11 dB. Clearly, such a signal will require a substantial power backup of the PA, leading to typically poor average modulation efficiency. Well, based on our ETH peer survey, we can also plot the modulation performance of reported 20 to 50 GHz silicon PAs versus their average output power. Most PAs here use high-speed 64-column modulations. We can see there is a huge gap between the modulation performance versus the continuous wave performance. The average output power of modulation performance is typically lower by 10 dB or more compared to the continuous wave performance. To improve it, we need high output power PA with better linearity and a better power combining. The average efficiency for the modulation is 1.7 times lower than the CW efficiency. This is where we need new PA architectures such as Doherty PA and out-phasing PAs, as well as better PAs with better linearity. Again, referencing the PA output power versus the array size table for the 5G applications, the expected average efficiency is typically 20%. So we can see that some of the recent PA designs have achieved this high modulation efficiency already. Now the goal is to further enhance this modulation efficiency and push the average modulation output power. Again, this is the place where advanced PA architectures such as Doherty and out-phasing PAs will be really critical here. The next challenge is array operation and the PA footprint, which is especially important for PAs to support 5G millimeter wave front-end module array applications. It is well understood that as we move to higher carrier frequencies for the same communication distance, the resulting path loss will degrade proportionally to the carrier frequency squared. At 28 GHz for 300-meter range of a typical urban cell, the path loss is 100 dB for line of sight to 170 dB for non-line of sight. At 140 GHz, the path loss for 100-meter range of channel is close to 120 dB. So therefore, array operation is absolutely necessary for these millimeter wave systems. A generic millimeter wave 5G transceiver front-end module array is shown on this page. It typically includes multiple array elements. Each array element includes TR switch, LNA, and PA, phase shifters or for element phase control, VGAs for element amplitude control, and beamformer on the same chip. Sometimes it also includes up and down conversion mixers and the error feeding networks. Some performance monitoring circuits are needed as well, but overall, it is a complicated system or integrated on the same chip. In practice, mobile wireless communication requires dual polarization, which means all the numbers and all the number of front-end circuits now need to be doubled to simultaneously support both horizontal and vertical polarizations. Moreover, considering multi-band and multi-standard operations, such as international roaming, each front-end array needs to support dual-band or even tri-band operations. We can see that the required complexity just increases quickly in such systems. A few recently reported arrays are shown on this page as examples. The first one is a 28 and 39 GHz 32 and channel TRX dual polarized and phase array FAM transceiver IC reported by Samsung in 2022. The total 32 TRX channels occupy 8.74 mm by 2.87 mm chip area. The second design is a 24 GHz 24 channel CMOS dual polarized TRX array for both 5G user equipment and base station application from Qualcomm. Sorry, it's 28 GHz. The 24 TRX channels occupy a total chip area of 5.97 mm by 4.95 mm. The third design is a 24 GHz to 30 GHz 16-element dual polarized TRX array reported by IBM. The 16 TRX channels occupy 8.6 mm by 5.6 mm total chip area. So as we can see, these 5G millimeter wave front-end arrays require compact millimeter wave PA solutions. In general, one TRX and front-end and the channel typically occupies somewhere between 1 mm squared to 0.5 mm squared, depending on the functionality and the performance. At the same time, the PA should deliver sufficient output power, higher modulation efficiency, and a wide carrier bandwidth, all of which need architecture innovations. The energy efficiency of the PA also directly impacts the thermal density of the array. The linearity of the PA is essential as well, so that additional power backoff or signal pre-distortion can be avoided for simplicity and array scalability. These requirements pose new challenges on millimeter wave PA solutions. The third challenge is the limited PA output power density by different technologies, particularly for 6G sub-millimeter wave applications. Well, when we are trying to quantify the power density, and we know that the device community often use the power density as a device saturated output power divided by the device size as watt per millimeter. Here, millimeter measures the peripheral size of the device. This metric depends on the device voltage, current, and the frequency. It is a widely used device-centric metric to compare intrinsic performance of different device technologies. However, a different device power and density can be defined as the saturated output power divided by the PA core area size as a watt per millimeter square. Here, the millimeter square measures the PA core area. It builds on the device-centric power density of watt per millimeter, of course. But it also considers other implementation factors such as backend quality, layout compactness, and PA circuit topologies. This is a circuit-centric metric, which is very useful to compare millimeter wave circuits and to plan system architectures. For example, we can use it to compare different technologies for their area efficiency to generate RF power at a certain carrier frequency. Also, if we know the watt per millimeter squared metric for technology at a certain frequency, for a given chip area, now we can estimate the achievable PA output power Pset. In the context of phase arrays, given array frequency, we will know that the array lattice size typically is defined as lambda 2 by lambda 2 with the lambda as the wavelength in air. If we assign a certain percentage of the array lattice area, let's say 20% for the PA, now we can estimate the achievable output power. Therefore, we can directly determine the required size of array for a given ERP, which will impact the total aperture size, system complexity, and the cost. Further, if we know the technology cost in terms of dollar per millimeter square, knowing its watt per millimeter square metric, we can directly estimate the cost to generate certain output power as a watt per dollar, which is also very useful for system planning. Using our power and amplifier survey, we can plot the reported PA watt per millimeter square power density versus the carrier frequency for designs higher than 90 GHz. We can see that the watt per millimeter square metric performance decreases versus frequency and output power level. This makes sense. Also, the indium phosphide PAs typically achieve the highest watt per millimeter square density due to their high device gain, while the gallium nitride PAs will achieve the highest saturated output power at these high frequencies, which also makes sense. However, we can see that some of the CMOS PA designs can actually achieve similar or better watt per millimeter square density than the gallium nitride PAs. This is kind of counterintuitive. Gallium nitride devices typically will have 20 times better watt per millimeter device level power density than the silicon devices. However, such a huge device level advantages are not showing up at the circuit level. This is mainly because of the technology difference between gallium nitride and the silicon processes. The CMOS processes can support a much higher layout density for both active circuits and the passive components compared to the gallium nitride technologies. The CMOS technologies also offer versatile backend options with 7 to 8 or even more metal layers. This enables ultra compact and high coupling passive structures, which further save the chip area. On the other hand, multiple research programs are now focusing on improving the active device power capability and the passive device and the packaging density, especially for the compound semiconductor technologies. So we should expect to see exciting results coming up in the next few years. In summary, to address these beyond 5G and 6G applications at high millimeter frequencies, the PA solutions should be both compact and energy and area efficient. This clearly requires new innovations at various levels, including devices, circuit systems, and packaging. Next, I will present several power amplifier candidate topologies and the recent design examples that are promising for 5G and 6G applications. The research in silicon-based millimeter PAs started roughly in early 2000. Interestingly, as of today, the basic Class A VPA topology is still the mainstream PA and topology being deployed in most millimeter wave systems, both in academia research and in industry products. I'm showing some Class A VPAs as design examples here. They offer good balanced and performance of efficiency, linearity, and modulation bandwidth. They are also the RF in, RF out PAs with no need for any real-time controls. Most importantly, they are very compact, which really eases the system integration. To boost the efficiency beyond the basic Class A VPAs, one approach is to explore harmonic terminations. Many harmonic termination PAs are narrowband. In 2011, Professor Steve Cribb's group started this concept of continuous mode harmonic tuning PAs, mainly for 3.5 compound PAs. But another work from Virginia Tech presented the class F inverse and the class F exchange PAs at ISCC 2014 for wideband applications. We also look at this interesting PA topology. Our goal is to substantially reduce the area of the continuous mode harmonic tuning network at the PA output. Instead of using a complicated network with many passive components, we are able to realize a broadband continuous mode class F inverse output matching network within only one on-chip transformer footprint. The parasitic effects of transformer are carefully explored and even enhanced to achieve the desired class F inverse harmonic tuning. The figure on the right shows the wideband load presented to the PA. The differential fundamental impedance is tuned around a desired constant conductance circle. The second order harmonic impedance is mostly reactive, but at around the high impedance level, while the third order harmonic impedance is tuned to the low impedance. And this is the combination of a desired class F inverse and the harmonic shaping. Since the PA output, the second order harmonic voltage is enhanced. To improve the PA linearity, the PA input is carefully terminated at the signal harmonic to lower impedance. This prevents the output signal harmonic voltage from being fed back to the input and remixing with the fundamental to generate IM3 tones and degrade the overall PA linearity. The PA schematic and chip microphotograph are shown on the left, and the work was presented at ISCC 2018. To further boost the PA large signal performance and achieve flat OP1 dB and PAE over a wide frequency range, we also look at the use of on-chip coupler as a wideband power combiner. On-chip transformer models are widely used for power combining, but they need to include many additional parasitic elements for accurate modeling. Moreover, transformer models restrict the structure to be used below the resonant frequency when the magnetic and the coupling is dominant. However, if we use coupler modeling, we can explore the coupling structures with wide and large turns to boost the coupling and the passive efficiency, and to really utilize its coupling both at the lower frequency for magnetic coupling and for higher frequency for capacitive coupling. An example coupler structure is shown here with 29 micron trace width and a 250 micron turn diameter. If we model it as a transformer, its self-resonant frequency is only 27 gigahertz. However, if we see that, and if we model it as a coupler, we can use it for wideband matching and power combining between 24 all the way to 42 gigahertz. The resulting real and imaginary impedance are well behaved, and the passive efficiency is more than 86% over 24 to 42 gigahertz, thanks to the wide and the large turns. Then we can use it as an output matching network for a single branch differential PA over the same frequency range. The chip area is very compact with only 0.21 millimeter square as the core area. This is highly desired for large-scale array applications. To further boost the output power at millimeter wave silicon PAs, the stacked transistor PA topology is proposed and demonstrated. The key here is to leverage various feedback and feed-forward and sometimes even direct driving networks to allow the gates of the stacked devices to swing. This reduces the stress of the stacked devices and allows more devices to be stacked beyond conventional cascade PAs. Therefore, the stacked PAs can have relative large optimal load impedance, which simplifies the output impedance transformation network and can achieve high output power and high PAE at the same time. In addition, stacked transition PA improves the power density of the power device core, typically by a factor of 2 to 3, depending on how many devices in stack and how efficient the stack design is. This potentially allows more compact integration of high power PAs. There are a few examples of stacked transistor PAs here, all achieving excellent performance. On the other hand, in order to boost the backup efficiency of an RF circuit PAs, this is typically achieved by active load modulation, which is essentially using multi-pass circuits that will modulate and pull each other to boost the overall energy efficiency. Fundamentally, there are two active load modulation schemes in general. One is the Doherty and the architecture. As an example, two amplifiers are connected using one impedance inverting network, for example, a λ4 transmission line at their output. At the low power level, only the main PA is on and it sees its optimal impedance. This just behaves as a one single pass PA. At high output power level, the auxiliary PA is now gradually turned on, and its output and the current combines coherently with the main amplifier and the current in phase at the output. So at the main branch here, it sees an increasing impedance due to the active modulation from the auxiliary PA. Then, after the impedance inverting, the main PA output actually will see a decreasing load impedance, which extends its linearity and boosts the backup efficiency. As a duality, the out-facing architecture has two constant envelope nonlinear amplifiers driving an one out-facing network. The vector combination of the two amplifier outputs will generate the desired output, the complex output modulations with varying amplitude. The technical challenge for these two PA architectures is essentially how to innovate their load modulation network that are typically bulky, lossy, and narrow band in operation. There have been a major focus on millimeter wave Doherty power amplifiers in recent years, from Ka band to E band, and now recently W band and D band. We have also been working on Doherty or Doherty-like power amplifier designs in silicon at a millimeter frequency. As an example, and one design from my group is this multi-band millimeter wave Doherty PA in 130 nanometer CMOS CG process. In one PA design, it covers multiple 5G bands at 28 GHz, 37 GHz, and 39 GHz for MIMO applications, and it provides backup efficiency enhancement at all of these three bands. It can be shown that the Doherty load modulation network relies on a combination of an impedance inverting network, IIN, and an impedance scaling network, ISN. However, most Doherty and the load modulation networks at RF or low gigahertz frequencies cannot be scaled easily to high millimeter frequencies. To address this challenge, we find that the IIN and ISN can be implemented using balance. If the balun input-output phase difference is plus minus 90 degrees, then the balun is an impedance inverter network. If its input-output phase difference is 0 or 180 degrees, it is an impedance scaling network. These two special baluns can be combined with the main PA and auxiliary PA cores and realize a high-efficiency Doherty PA at 60 GHz. In recent years, and Professor Steve Grip's group proposed a load-modulated balanced amplifier LMBA concept. This LMBA concept uses a 90-degree coupler at the output and feeding the two quadrature ports using two main PAs. The typical isolation ports now of the 90-degree coupler now is driven by a control amplifier that essentially functions as the peaking amplifier. If we assume the output network is driven by the current sources, and by solving the current voltage relationship, we'll see that the loads of the two main PAs are now modulated by the current of the control amplifier to achieve backup efficiency enhancement. The unique advantage is that it supports a broadband active load modulation, only limited by the 90-degree of the coupler itself. This is why this LMBA topology is becoming very popular among 3.5 compound PAs for gigahertz applications and some millimeter wave silicon PAs. On the other hand, it is restricted to single-ended PA operation, or one needs to use multiple baluns or differential quadrature couplers. Both will limit the bandwidth and potentially add more loss. Further, the input-output 90-degree coupler will increase the PA size and the form factor, making it difficult for large array applications. Recently, Samsung reported a single transformer-based compact Doherty PA for 5G millimeter wave front-end array applications. The design replaces the λ4 T-line impedance inverting network for the main PA by a synthetic and LC lines. which then allows the auxiliary PA to be placed in line with the main PA to save the silicon area. Moreover, the remaining Doherty PA automatic network now is realized using one transformer. Combining these circuit innovations, one Doherty PA can be implemented using one single transformer. The PA core area is 240 micron by 640 micron without the input balun, or 240 micron by 810 micron with the input balun. The compact Doherty PA is implemented in a large-scale array with 32 TRX channels and on the same chip. The PA achieves its peak PAE of 30% and at 27 gigahertz. It also supports wideband 5G and FR2 64 QAM modulations from 1cc 100 megahertz to ACC 800 megahertz. The averaged PAE varies from 20.2% to 18.1% for different modulation complexities. Next, I would like to introduce a few recent PA designs for D-band 6G applications. Based on the PA performance surveys, we see that the devices are often the fundamental limitation factor to scale the front-end electronics over frequencies to D-band and beyond frequencies. This is certainly very true for power amplifiers. It is well known that for a perfectly neutralized differential pair device, its output gain will drop as minus 20 dB per decay over the frequency. So therefore, as the rule of thumb for millimeter wave and circuit designs, if one tries to achieve power amplification for frequencies around Fmax over 2, this gives roughly 6 dB gain per stage theoretically. Although this is certainly possible, the active device gain will be very limited considering the additional passive loss and the mismatch losses in practice. However, if we want to achieve high efficiency and decent OP1 dB linearity, it is important to operate below Fmax over 4, the frequency. This gives 10 to 12 dB gain per stage, and this means for high efficiency 140 GHz PAs, we really need devices with Fmax at 560 GHz or above frequency. Keeping these rule of thumbs in mind, we can examine the state of the art of the device technologies in terms of their Fmax and FT. Then we will know the maximum operating frequency they can support in practice. This slide shows the device FT and Fmax summary plot from John Strange and Ned Cajon's past presentations. The x-axis is the technology nodes, while the y-axis shows the FT and Fmax and the frequencies. It is interesting to see that the Fmax of the CMOS device will plateau at around 450 GHz. Therefore, although they can support power amplification and the 200 GHz for some designs, their high efficiency operation will happen below 100 GHz and double band frequency. This matches several recent CMOS PA designs at the D-band frequency where the maximum PAE will be around 15%. A high value compared to their peer designs for this efficiency, but they are still quite low compared to CMOS PAs at lower frequency. This again is fundamentally limited by the device gain. On the other hand, the Fmax of the CG devices can reach over 700 GHz due to their vertical and lateral device scaling, much higher than the CMOS devices. This shows that the CG devices are very promising to realize high efficiency D-band operation for 6G applications. Since it is identified that the device gain is often a limitation for high-frequency amplifier designs, and there has been a continuous research exploration on passive embedding schemes to boost the device gain for a given technology. This work from UC Davis in 2017 proposed a systematic method to construct a passive embedding network which will wrap around a transistor and boost its gain to Fmax to Gmax that is close to 4 times of its unilateral gain, as well as an unconditional stability. It lays the theoretical foundation of gain analysis and the embedding network designs, which guides many following explorations on close to Fmax gain boosting amplifier designs. As a proof of concept, 257 GHz amplifiers are implemented and demonstrated using 65 nanometer bulk CMOS process with the best Fmax of only 350 GHz. The existing device embedding can achieve device gain as 4U, but only supports one single frequency. Another line of research is reported from KAIST and Korea. Multiple papers from this group report 3-line embedding networks to achieve Gmax gain peaking at dual frequencies for wideband D-band and for wideband D-band and G-band applications using 65 nanometer bulk CMOS technologies. The design also can be implemented as a cascadable and multi-stage designs and nested embedding networks. However, it is still single-ended and it forces the same DC biasing point of the device at the device the input and output, which will limit its the efficiency gain and the linearity designs. Well, we explored another method called complex neutralization to broaden the bandwidth for this gain enhancement. Essentially, we create high-order neutralization networks to also achieve double peak device gain peaking at 2 frequencies, and then in total supports broadband operations. Our complex neutralization techniques also absorbs routing parasitics and supports differential operations. We implement this scheme using Teledyne 250 nanometer indium phosphide devices and eventually achieves 35 to 100 GHz PA operations. In addition, in this work, we also report that 180-degree coupler balun can be used to implement load modulation PAs. Moreover, it is shown that a series cascade of 2 180-degree coupler balun realizes a series Doherty load modulation network, which achieves a wideband Doherty PA operation. The 180-degree coupler balun and also offers the advantages of differential PA operation and equal power dividing without the gain compression of the PA. Both will boost the performance of this fully integrated PA. We implement both the complex neutralization technique and the coupler balun based Doherty PA using Teledyne 250 nanometer indium phosphide devices and eventually achieve 35 to 100 GHz and Doherty PA operation. The results demonstrate the PA superior performance compared to the state-of-the-art. Another work from POSTEC also explores using lumped components to form embedding network for differential amplifier circuits. The embedding network is composed of a CLC path. Its 2 series capacitors allow for the decoupling of DC biasing of the input and output of the transistors so that the gain, efficiency, and output power can be optimized. Overall, it achieves dual peak gain and peaking for wideband device level gain boosting. It is implemented and demonstrated as a D-band PA in 28 nanometer CMOS FDSOI technology. The GMX boosting and the gain boosting concept is also explored at the IMEC and is implemented in a D-band low power FMCW radar transmitter. It adopts the frequency multiplied by 9 topology and is implemented in 28 nanometer CMOS. Power combining is explored to boost the output power of D-band PAs as well. A recent paper from UC San Diego combines 4 differential PAs at a D-band frequency using 45 nanometer CMOS SOI technology. It achieves 17.5 to 19 dBm P-set and 14.2 to 12.1% peak PAE. There has also been explorations on Doherty PAs at the D-band frequencies. As another design example, an ISC 2020 paper from Tsinghua University, Beijing, China, and MIT, US utilizes the slot line structure to realize the impedance inverting and impedance scaling functionalities. The PA is implemented in 130 nanometer CG technology, and the PA is tested with both CW and the modulation and testing, showing their state-of-the-art performance. And there are many ongoing explorations on high millimeter wave PAs at the D-band and even higher frequencies now. Due to the limited time here, I cannot cover all the reported work. However, it is clear that this is an exciting field of research, I'm sure we'll see more exciting results reported in the next few years. Finally, I would like to conclude my talk. Power amplifiers are the key building block for wireless systems, as they typically govern the energy efficiency, communication distance, bandwidth, and the data rate of the system. We have reviewed the state-of-the-art performance of modern PAs with a particular focus on millimeter wave PAs using silicon technologies. We also introduced several key challenges for 5G millimeter wave PAs and 6G D-band PAs. Finally, I reviewed several recent PA candidate topologies and design examples for 5G and 6G applications. I want to emphasize again that as the wireless systems evolve continuously, new applications with new challenges are emerging, so the field of power amplifiers has plenty of space for circuit innovations. With that, I would like to thank you for watching my IMS 2023 primer video on modern wireless millimeter wave power amplifier designs for 5G and 6G wireless applications. Hope we will enjoy the IMS 2023 conference. Thank you.